Now, assuming that there are no layer 3 transport problems between the sites, we should now see that when the tunnel comes up, the two edge devices form an ISIS routing adjacency over the tunnel that they're going to be using to advertise the MAC addresses of the end host that we want to bridge. And this is one of the key functional differences between an OTV tunnel and other types of layer 2 overlay. So let's say, for example, we go back to our logical topology. As I mentioned, there's multiple different options we could have for this data center interconnect in the middle. So in our case, we're running OTV, but we could also run just dark fiber. And over the dark fiber, we could run regular Ethernet. We could do like a VPC between multiple sites, or we could run Fabric Path if we want to. We could also be running over an MPLS layer 2 VPN, which this could be something like a virtual private LAN service, a multi-point tunnel, or it could be a point-to-point circuit like an Ethernet VPN, an EVC, Ethernet Virtual Circuit. Now, for these types of designs, okay, so for now exclude Fabric Path because we talked about Fabric Path has special forwarding rules. But with regular Ethernet over the overlay, how would one data center learn the MAC addresses of another one? As we talked about regular Ethernet bridging, when the source doesn't know how to get to the destination, what does it do? We just send the traffic everywhere, right? So in the case that we're doing bridging over either an MPLS layer 2 VPN or dark fiber, it means that both data centers would be in the same failure domain for the layer 2 network. So it means if there's a spanning tree convergence event in one side, it's going to affect the other data center. Or if I start to flood all sorts of MAC addresses on one side, they're going to appear in the MAC address table of the other data center. So even if we have hosts that we don't want to send across the data center interconnect, the switches are going to have to know about all MAC addresses everywhere. So this now starts to become a scaling issue, because not only do I need to account for all of the end servers that I have in my DC, but it's also going to have to account, we would also have to account for all the MAC addresses that are in the remote one. Now this is assuming we're not doing an OTV tunnel, we're doing just a regular layer 2 extension. In the case of OTV, this is optimized by advertising in the routing control plane with ISIS, the route to the other MAC addresses in the other data center, so it means that we don't have to do unknown forwarding. So we will always know about our own local MAC addresses based on regular flooding rules, and we'll know about the remote data center MAC addresses based on an ISIS advertisement. Then depending on which host we actually want to exchange traffic between, we already know where the destination is located. We don't have to do any unknown flooding. So it's an optimization of not only the control plane, but it's an optimization of the data plane, that we won't have all sorts of like unknown ARPs that are going between the two different DCs. Okay, so next let's look at the just show OTV. Okay, it says overlay, the VPN status is up, and we are authoritative edge device capable, yes. Okay, these two fields together, this basically means that we're able to forward traffic over the tunnel. We'll come back and talk about these details a little bit later, but at this point, we should be able to see routes to the remote data center. And the way that we could see this is by looking at the show OTV route. Now, if we correlate the OTV routing table to the MAC address table, any MAC addresses that we are learning locally, so that are on our directly connected ports, we should see those associated with physical interfaces. Like in this particular case, we see that this address, 530A, is located on a physical link on Ethernet 2/27. If the MAC address is located remotely in the other data center, we would see the next hop as the authoritative edge device on the other end of the network. So if this value here doesn't show us a physical interface, that tells us that we're going to be routing on the overlay tunnel. So in our particular case, let's go back to the servers that we were testing connectivity between, and we're going to do a ping between them. And I think what I need to do first is to clear out the ARP cache. So let's say ARP-D, and then we're going to ping the destination, 10.0.0.8. Okay, we do have reachability to it, and let's take a look at the 5Ks and look at what the MAC address table says. So let's show MAC address table dynamic for VLAN 10, and it says that I know these addresses. Okay, so these are the two servers. I know one of them out my physical port connecting to the server, and I know another one out the port that goes up to the 7K. So in our physical design, right now the traffic is going in this direction. It came in E11, we flooded it out E16. From 7K7's point of view, if we look at the show MAC address table dynamic for VLAN 10, we see that MAC address, which was the 423C, it says it's located out the physical port, which is E227. Now, once we learn about this source MAC address, and again, normally we learn about the source MAC address because they are sending an ARP request, and inside the ARP request, we have their MAC address, so MAC address A is encoded in the source of the packet. So now 7K7 says that MAC address A is located on port E227. Okay, this is a local port. Now over the OTV tunnel, we are going to advertise this MAC address as an ISIS route. So a route just as like you would have in regular layer 3 IP routing, that you have a connected LAN segment that's on the 10 network, you have a loopback that's 1111/32, and you're advertising it into OSPF or to EHRP. But in this case, the route itself is a MAC address destination, it's not an IP address destination. So now on the other end of the tunnel on 7K8, if we look at the show OTV route, we now know that this particular server destination, 423C, is located on the overlay, and the next hop is this device that we have an adjacency with. Specifically, this device, we know where they're located because if we look at the show OTV ISIS adjacency, we know that we have an adjacency with this particular box, and their destination is on this particular interface, overlay 1. So what also becomes different about the OTV tunnel as compared to a regular point-to-point GRE tunnel is that OTV can be a multi-point tunnel. So you have DC1 configuring the overlay tunnel, but it could be to multiple remote data centers at the same time. So in order to account for this in the control plane, this is the reason that multicast is needed in the middle. Because the ISIS hello packets, when we're actually trying to establish this routing adjacency, we basically take the ISIS packet, we're putting it in a GRE tunnel, and then the destination is that multicast address that we defined as the multicast control group. So as the name implies, this is for tunneling the control plane. Once the devices establish the reachability with each other, they then know what is the unicast source address that the other end of the other endpoint of the tunnel is using. Now, in this case, it's simple because the devices are directly connected on the layer 3 port. But in most, in many designs, not in all designs, but in many designs, there might be other layer 3 routing devices in the middle. Like if we're going over an MPLS layer 3 circuit, or if we're going over the internet, there's going to be other routers in the middle that need to route the packets between them. So this is what I meant by, from a configuration point of view, when you specify the OTV tunnel, you don't say who it is going to. You just say where is it coming from. It's coming from this interface, and then we're going to find the destinations by using this multicast address in the control plane. Okay, there's a question here. Why was ISIS used for OTV and fabric path over EHRP? The reason why is that ISIS is encapsulated directly at layer 2. It doesn't require another layer 3 transport under it. So when you look at the frame format of ISIS versus something like EHRP or something like versus OSPF, you would have your Ethernet header, at the bottom, and then you would have your IP packet, and then you would have your OSPF header. Okay, then you have the actual data, which is the link state advertisements. Or in the case of EIGRP, likewise, we go over IP, and then we go over whatever the layer 2 is. In the case of ISIS, it is directly encapsulated at layer 2. The reason why is it is its own protocol stack. So IP and ISIS, even though ISIS is used to advertise IP routes, the protocol itself is not an IP protocol. It's an ISO CLNS protocol. So what this means is that when they implemented FabricPath and when they implemented OTV, they're skipping the step of having to configure IP networking between the upper layers and the lower layers. This is the reason why on the overlay tunnel, you do not need to put an IP address, because the routing protocol directly encapsulates inside of Ethernet. So specifically the frame format, and I have a real detailed blog write-up on this. If you guys search for just OTV GRE, it's OTV decoded a fancy GRE tunnel. And in this post, I talk about specifically what does the data plane encapsulation format look like. And when you look at the full header, it is, and I don't know if I have it written out here other than, so let's look at something in the data plane like a, okay, so here this is the ISIS routing packets that are being exchanged over the tunnel. So we have an Ethernet frame that has an IP packet inside of it. IP is encapsulating GRE. GRE is encapsulating MPLS. MPLS is then encapsulating Ethernet, which has the ISIS header inside of it. So it basically means that the frame looks like this. You have your outer Ethernet, you have your outer IP header, the outer GRE header, the MPLS tag, then you have the inner Ethernet packet, and then you have whatever your payload is. So the portion that we are tunneling is this point on. So in terms of ISIS routing, the routed packet would be this first portion here. And then directly inside of this, we would have ISIS. And ISIS is advertising the MAC addresses about what you want to extend. If we were to use OSPF or to use EIGRP for the same type of point, the protocol would have had to been extended, and ISIS already has these extensions built into it. But additionally, we would have to configure either manually or through some automatic method another IP overlay network inside of the tunnel. Or the same with FabricPath. We would have had to have the routing in IP, then in Ethernet, then in FabricPath. So it basically cuts out the overhead between these two and the rest of the payload that you don't need IP. So you'll see that the configuration is fairly simple for the feature, where we simply make sure that whatever number we are extending, this cannot be either the site VLAN or the, or basically it just cannot be the site VLAN. So this is whatever we're trying to bridge inside of the tunnel. This is the tunnel source interface. This is how we're finding the other endpoints of the tunnel. Now there is an alternate config for this, an alternate design. If your transport does not support multicast, you can tunnel the control plane inside of a unicast, but that assumes that you know who the destination of the tunnel is. Because notice here again that the difference between regular GRE and this is that there's no tunnel destination command configured. But there is an option where you can specify on the overlay that there's an OTV adjacency server. And the adjacency server is basically you specify what's the other end of the tunnel, and then you use this in order to figure out who are the different endpoints. So let's say, for example, you have three different data centers you're trying to tunnel between. You have DC1, DC2, and DC3, what you would do is say that the adjacency server is on this DC. So this one registers with it, this one registers with it, and they now learn implicitly each other's IP addresses because the adjacency server has that information registered. So now if we have a source A that's trying to get to B, they know that they can directly tunnel to each other because they learned about the endpoints by using the adjacency server. So without this, you're assuming again that the layer 3 network supports multicast, where in a lot of designs it does not support multicast. So either you would have to buy that service or use this as a workaround. Now, in terms of other features of the tunnel, beyond the optimization of the unknown flooding, because again, the difference is when you look at the show MAC address table and you compare this to the other side, or actually, let's say this between, we would need to look at this on all of the switches. Let's look at the show MAC address table, dynamic for VLAN 10. And we'll see that not all of the tables are equal. The reason why is that when I go to flood an address within my own data center, the edge device advertises the MAC address over the tunnel, but it doesn't flood the packet across. If someone on the other side wants to reach the destination, since we know where the source and destination MAC addresses are located, we can send them directly as unicast. But it cuts down on the unknown frames, and it also cuts down on the amount of ARP traffic that we would normally flood over the tunnel. So the edge device keeps a copy of the local ARP cache on behalf of the end hosts. And you can see this if you look at the show OTV ARP and neighbor discovery cache, where right now I don't believe the end hosts ARPed for each other. I think they already had I think they already knew their addresses from before. But if we delete the ARP cache and then ping between the servers, we should see that now the edge device is caching this information. So any other device in the remote data center, if they send an ARP request and we see the destination is 10008, we don't need to flood that information across the tunnel. We can locally reply with what information we have in the cache. So the idea is that you want to keep as much traffic local as you can. You only want to tunnel to the remote side if it's actual data traffic going there, not if it's just unknown packets or if it is control plane packets. So again, you could accomplish the same thing by doing either just a point-to-point dark fiber or by doing something like MPLS Layer 2 VPN. But the advantages are it keeps spanning tree local, so you don't have the failure domain spread between the different sites. It allows you to do multi-point bridging, so you can have multiple edge devices for redundancy, and it automatically prevents the loops between them. And it has these other optimizations in the data plane. So it's stopping the unknown frames from flooding. It's advertising the MAC address table as routes as opposed to just flooding the packets everywhere. And it's also optimizing the ARP cache on the edge. There's a question, is there a way to set the ISIS router ID under the OTV process? You can customize ISIS. If you go to globally, it would be, you say OTV ISIS, and we have the default process, and we'll say this is for VPN overlay 1. Okay, that's the tunnel we had configured. And the router ID would be the network entity title. So in the case of something like OSPF, you use an IP address as the router ID, like 1234. In ISIS, it's called the network entity title. It comes from the ISO NSAP addressing, which is part of that legacy CLNS protocol stack. So the router ID would look something like this. It would be like 00, 0.00000000001.00. That would be the minimum length for the ID. This portion here is called the N selector. This has to be 0. This is called the system ID. That's the router ID within the area, and then this is the area address. Normally, you wouldn't really need to set this though, because everything happens automatically behind the scenes. The only one thing that is necessary for this is that it's a unique value. So as long as the routers choose different net addresses to begin with, then they should be able to form an adjacency and advertise the routes. So it's kind of like an OSPF. If you had overlapping router IDs, you would not be able to advertise different routes to each other. If we were to then look at the show OTV ISIS database detail, where in the case of Fabric Path, we saw this for the there we go. In the case of Fabric Path, this is where we saw their interconnections between the switches. In the case of OTV, what we would see, and let me send some traffic between the servers again. Now, in order to prevent loops, there's a delay. Anytime you make a change to the tunnel, the router has to wait for an election process before it starts to forward. And you can see this if you look at the show OTV VLAN. So we won't actually be able to send anything for a couple more minutes. But what we would normally see in this output is when you look at the ISIS database, you would see the actual MAC addresses of the end servers, and then you would see a metric associated with them. So theoretically, if you had multiple overlay tunnels, you could prefer one over the other by setting the metrics. Just like in the case of Fabric Path, you could set the ISIS metric at the interface. But normally, these options, you just leave them as the default. It's just that as long as you have layer 3 unicast and multicast reachability, it should automatically find the other endpoints of the tunnel and then automatically advertise all of the MAC addresses in the table, but only actively use the ones that you want to forward bidirectionally.